Welcome back. Today we're looking at part one, getting started with big data. It covers the basics, evolution, the V's, core tech, solid groundwork, but we want to sharpen it for a technical reader. Let's dive right in.
Okay, so first up, the introductory definition of big data, while it covers the 4 V's, really needs to elevate the conversation much faster for a technical audience by hitting the critical engineering trade-offs those V's actually force.
Right, okay. I get that. Technical folks don't want definitions spoon-fed, but aren't volume, velocity, variety, veracity kind of the standard starting point, the convention? Is it really that bad to start there before getting into the compromises? What's lost?
Well, what's lost is the urgency, the so what for an engineer. They understand velocity as a concept. The text itself even says, just listing the V's can be misleading and overly simplistic.
True, it does say that.
But the weakness is it then kind of hangs around describing these challenges like, oh, dealing with messy data types is hard, without immediately saying, look, this forces us to make specific, sometimes painful, architectural choices to achieve scale.
Ah, okay. So the suggestion is link those V challenges directly to giving up traditional guarantees, like ACID, for scale and speed. Basically frame big data as engineering compromise from the start. Less definition, more problem statement.
Exactly. For this audience, big data means accepting, well, let's call them different standards to handle the sheer scale and speed. It's a trade-off. That needs to be clear up front.
Can we make that super concrete? Like an example? How do you pivot from a V to a trade-off in, say, one breath?
Sure. Take velocity. High velocity. Instead of just saying data arrives fast, pivot immediately. Explain why getting that low latency you need in distributed systems means you often have to ditch strict transactional integrity.
Okay.
So you say something like, the sheer velocity demands such low latency that traditional guarantees like ACID consistency often become impractical. We prioritize ingestion speed, accepting eventual consistency across potentially thousands of nodes. See? Connects the V directly to the engineering choice.
That definitely lands harder. Hits the architectural implication right away. And you could do the same for veracity, right? The whole dirty data issue?
Absolutely. Connect low veracity, the fact that incoming data is often messy, likely to be quite dirty, as the text says, directly to the trade-off during exploratory analysis or real-time ingestion.
How so?
Well, you explain that integrating this dirty data with cleaner operational data forces a choice. Either enforce strict integrity, which would slow everything down, or reject data, or prioritize speed and ingest the potentially flawed data. Because the cost of real-time cleansing is just too high for the required velocity.
It shows why veracity matters architecturally, not just conceptually.
Right. It sets up the whole why for the rest of the technical discussion. It defines the problem as these necessary compromises, which then justifies the architecture needed to handle them.
Exactly. Which leads us nicely into that architecture discussion. If the first fix is about framing the problem as trade-offs, the second is about structuring the solution, the architecture itself logically.
Okay, let's look at that structure. The way the big data architecture is presented needs to follow a strict, logical, bottom-up approach. You really have to nail down the foundational infrastructure layers before bringing in the higher-level processing stuff.
Yeah, this is a key structural weakness we saw. Chapter 1 introduces the conceptual stack, which is fine, but then it jumps ahead. It starts talking about specific tools like MapReduce, Hadoop, Bigtable. Before it's really established the underlying layers that depend on, like the redundant physical infrastructure or the operational data sources. It's like discussing the roof shingles before you've even poured the foundation.
And that skips the crucial why, right? A technical reader knows what Hadoop is, probably, but they need to understand why it's necessary, why that specific kind of software exists, based on the constraints of the layers beneath it. It feels out of order, disorienting.
Totally. So the suggestion is straightforward. Restructure it. Start at layer 0, the physical stuff, and move upwards. Use the requirements and limitations of each layer to justify the existence and nature of the next layer up. Build the story of the platform logically.
Okay, actionable. How do we start that sequential build? What comes first?
You absolutely have to start with the redundant physical infrastructure. focus purely on the reality of distributed commodity hardware. That means failure isn't an if, it's a when.
Right.
So, establish the need for resilience, redundancy, elasticity first. Hammer home that big data systems must be built assuming component failure and designed to scale out horizontally on cheap standard hardware. That's the bedrock.
So system survival comes before data processing, failure as the default state, not the exception.
Precisely. And once you've established that distributed, failure-prone physical model, then you can explain why the operational data sources layer has to function the way it does.
How does the physical layer dictate that?
Because the underlying hardware is distributed and failure-prone, the data sources sitting on top must also be designed for massive scale supporting thousands of users, blending structured and unstructured data, and they need inherent fault tolerance. The physical constraints directly shape the requirements for the data layer.
Makes perfect sense. The data layer inherits the characteristics of the physical layer it relies on. Physical justifies operational.
Yes. And only then, once you have this robust, distributed foundation, the resilient hardware, the scalable, fault-tolerant data sources, only then do you introduce the specialized software like MapReduce or Hadoop.
So now we explain Hadoop.
Now you explain how it leverages that specific infrastructure. You show that this software exists precisely because it knows how to manage complex jobs efficiently and cost-effectively across that particular type of failure-prone, scale-out hardware. The architecture unfolds layer by layer, driven by necessity.
Okay, that feels much more logical. Let's shift gears slightly. Chapter 3 covers the history of distributed computing, DARPA, RPCs, up to modern nodes. It's interesting context, but why is tying that history specifically to economics so vital for this audience?
Okay, so while that historical context on distributed computing is a good background, the material needs to draw a much stronger, more explicit line connecting those historical challenges, like high latency, to the specific economic and technological breakthroughs that actually enabled modern big data architectures.
Got it. So the weakness isn't the history itself, but its payoff. It mentions the changing economics of computing, but maybe too briefly. Like for an expert reader, that history needs to land with a really strong "so what?" regarding today's systems. Why did things shift so dramatically?
Punch home the relevance. The suggestion is to really emphasize that the current model, commodity servers, sophisticated software automation, wasn't just a neat idea. It was an economic necessity.
A necessity driven by what?
Driven by the utter failure of the older proprietary approaches, like vendor-specific RPCs, to handle the scale and latency demands of modern data. The history needs to clearly explain why the industry was forced to pivot away from expensive, locked-in systems.
Right. Place the shift in that context. So let's focus on that failure point. You mentioned RPCs. How exactly did those older proprietary solutions hinder scale?
Well, fundamentally, they weren't standardized. That created vendor lock-in, which is always bad for cost and flexibility. But critically, they just couldn't solve the latency problem effectively for truly large-scale distributed processing. Enterprises ended up having to buy bigger, more expensive, specialized boxes because the software couldn't efficiently manage clusters of cheaper machines.
Okay, so the old way hit a wall, and the breakthrough wasn't just cheaper hardware becoming available, was it? It was a combination.
Absolutely critical point. The text needs to explicitly link two things happening at once. Yes, the plummeting cost of commodity hardware and the simultaneous innovation in software automation.
The software side being things like automated load balancing, failure recovery.
Exactly. That software layer, the intelligence that could automatically manage, optimize, and recover jobs across huge clusters of unreliable commodity hardware. That was the true enabling breakthrough for things like Hadoop. It let companies finally ditch the expensive, specialized gear and embrace horizontal scale-out, solving both the cost and the latency problems. The history has to build to that conclusion.
And building on that, let's talk latency again. The text mentions nodes, groups of networked computers working together. It needs to really clarify how this model directly tackles that persistent problem with latency that dogged earlier distributed systems. How do nodes fix it?
They fix it by smashing bottlenecks and enabling massive parallelism. Instead of funneling everything through one potentially overloaded central point or a few big ones, you partition the work across hundreds or thousands of nodes working concurrently.
So processing happens closer to the data, in parallel.
Precisely, it fundamentally changes the latency equation. The entire discussion around distributed computing history should really build a case for why this scale-out, commodity-based architecture became the inevitable dominant solution to the economic and latency pressures of dealing with modern, massive datasets.
Okay, this feels like a much stronger, more compelling narrative for a technical audience. So just to recap the main action items for the author. First, pivot quickly from just defining the V's to explaining the hard architectural trade-offs they force, speed versus consistency being a key example.
Right, frame the problem first.
Second, rebuild the architecture discussion strictly bottom-up. Start with the necessity of resilient physical infrastructure, then the data sources it enables, then introduce frameworks like MapReduce as solutions tailored to that specific foundation.
Build it logically, layer by layer.
And finally, make that distributed computing history really count. Explicitly connect the dots between the failure of older proprietary high-latency systems and the economic necessity that drove the shift to today's commodity hardware plus smart software automation model. Show why nodes and parallelism were the answer.
Nail the so what of the history.
Exactly. These changes should significantly strengthen the material for its intended computer science audience. We definitely encourage refining the text based on this and sending it back our way. We're keen to see the next version.